What is an electric field? It is a region of space in which an electric charge experiences a force. Draw a diagram representing the electric field around these two small conducting spheres. Now, the important thing is that these spheres are not the same. Although they have the same charge, they don't have the same magnitude of charge. So, what you've got is you've got 3 and 5. It's from positive. If we've got the same shape, we're going to have that kind of a shape. And it's from positive to negative, so your arrows will all go away. But you also need to show quite clearly that the plus 5 has got a much higher field density than the plus 3. Along the line joining the two small spheres, there's a point P, which is 10 millimeters from the plus 3. So this is 10 millimeters. We've been told that they are 40 millimeters apart, so this is 30 millimeters. Show that the magnitude of the resultant electric field is. So the first thing that you need to do is you need to say E is equal to K Q over R squared. Then you need to say 9 times 10 to the 9 multiplied by 3 times 10 to the negative 9 over, the distance is 10 millimeters, so it's 0,01 squared. That is then equal to 2,7 times 10 to the power of 5 to the right. How do I know it's from to the right? Because it is from positive towards negative, which means that at this point P, it is towards the right. It is away from that positive charge, because we are only interested in what's happening because of the 3 nanocoulomb charge. Now if I take a look at what's happening because of the 5 nanocoulomb charge, we get the following. Same equation, this time I substitute in 9 times 10 to the power of 9, 5 times 10 to the negative 9, and 0,03 squared. And I land up with 5 times 10 to the 4, and this time I'm saying from positive to negative, so it is away from positive. This time it is to the left. And my units in each case are newtons per coulomb, but we'll get that into the final answer. Now I have to say big number, 5 times 10 to the 4, minus small number, 2,7 times 10 to the 5, is equal to 2,2 times 10 to the 5 newtons per coulomb, and that you have managed to prove. We've got this positive charge. We've been given a value for this charged sphere. The charge is suspended, another charge is suspended from a light inelastic string, and it's brought close to Q. That gets repelled until the string makes an angle of 10 degrees with the vertical. The center of the two charges are now on the same horizontal level, and they're 5 centimeters apart, and then they give you a mass of Q. Calculate the magnitude of the electric field strength where Q is due to the electric field caused by P. So we don't even care about anything except for E, electric field, is equal to K Q over R squared, and that's 9 times 10 to the 9 multiplied by 4 times 10 to the negative 9 and divided by 5 centimeters to 0,05, and we have to square that, and I land up with an answer of 1,44 times 10 to the 4 newtons per coulomb. And they only wanted to know the magnitude, so we don't have to give a direction. Then they say draw a suitable labeled triangle using the triangle law for the forces in equilibrium. Well, I know that there's a weight acting down, Fg. I know that I'm repelling this with an electrostatic force, Fe. And I know that there is a tension in the string over here, T. If I pick those up and put them into a diagram, I land up with a downward Fg. When I'm asked to label, actually I should write the whole word out, weight. Then I have an electrostatic force. Sorry, I'm running out of space there. Electrostatic force, and then I'm going to have a tension over here. angle between the tension and the vertical is equal to 10 degrees. With that 10 degrees, I've got a hypotenuse, an opposite, and an adjacent side now. And then it says, hence determine the magnitude of the electrostatic force. Well, the first thing I need to do is decide what is this weight over here. And it is going to be, I've got to go to kilograms, which means it's 0,12348 times 9,8. And that turns out to be 7,84 times 10 to the negative 4 newtons. And then I'm going to put this into, so that means that I know the weight, I know the weight, and I know an angle, so I know the adjacent, and I'm looking for the opposite. So I'm going to use tan of 10 degrees is equal to the opposite over the adjacent, and I land up with the electrostatic force being equal to 1,38 times 10 to the negative 4 newtons. And then it says calculate the magnitude of the charge on Q. Well, now that I know the electrostatic force, I am able to say that I know that charge is equal to force divided by electric field. I've got a force, and I know the electric field at that position. I've been given it, I calculated it earlier, 1,44 times 10 to the 4. I could have also done this with F is equal to KQ over R squared. It was possible to get the same answer, and I land up with 9,6 times 10 to the negative 9 coulombs. Looking at question 7, because question 6 is very long, and we'll do it separately. So over here, I am asked, I'm told hematite is an important ore of iron, blah, 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 and here is the equation. How many grams of iron can be produced from that much hematite? So I'm going to say, I'm interested in that. I know this number of moles is equal to mass over molar mass, which is equal to 1,000 grams, divided by the molar mass of hematite, which is going to be 56 plus 56 plus 3 times 16, and that turns out to be 160, and that is equal to 6,25 moles. So I've got Fe2O3 is to Fe as 1 is to 2, so you land up with 6,25 is to 12,5, and then I go mass is equal to number of moles times molar mass, 12,5 multiplied by the molar mass of just iron is 56, and I land up with 700 grams. Calculate the volume of carbon dioxide formed. So I've got the same number of moles here, but this time I'm going to deal with carbon dioxide, and therefore iron oxide is to carbon dioxide as 1 is to 3, and therefore 6,25 is to 18,75, and I now am interested in a volume. They haven't been clear and said that it's at STP, but you can certainly assume STP. It's a reasonable assumption under the circumstances. They're looking for a volume of gas. V is equal to number of moles times molar volume. So that's 18,75 multiplied by 22,4, and I land up with an answer of 420 decimeters cubed. Seawater contains, among other things, magnesium sulfate. What is a solution? It is a solute. It doesn't say what is a standard solution. It says what is a solution. It is a solute dissolved in a solvent. Write down the formula of the ions of the solute magnesium sulfate. The ions are Mg2 plus and SO4 2 minus. Those are the two separate ions. Calculate the mass of magnesium sulfate that you would need to dissolve in a container of that volume to prepare a solution of that concentration. Not terribly difficult. We're interested in number of moles first. Number of moles is equal to concentration times volume, which is 0,25 multiplied by 0,2, because I have to change the 200 centimeters cubed into 0,2 decimeters cubed. And that turns out to be equal to 0,05 moles. And then if I need a mass is going to be equal to number of moles times molar mass, 0,05. And the molar mass of magnesium sulfate, MgSO4, turns out to be 120,3. And I land up with an answer of 6,02 grams. Now it says what volume of that solution is required to make up 500 centimeters cubed of a different solution. So the first thing I'm going to do with my standard solution is I'm going to say number of moles that I'll have at the end is equal to the concentration times the volume. 0,15, this is at the end, and the volume at the end is 0,5 decimeters cubed. And so I land up with 0,075 moles. That must have come from somewhere. Where did it come from? It came from this solution over here. So I now say volume is equal to number of moles over concentration, 0,075 divided by 0,25, which is the new concentration that I'm looking for. Sorry, the old concentration, the original concentration that it all came from, and I get 0,3 decimeters cubed. It doesn't ask how much we added. It just says what volume would be required. It doesn't say what's added, what's taken away. So how much of this would you need? I would require 0,3. I would have to add another 200 centimeters cubed in order to get up to 500, but that's not what they asked in the question. In the Haber process, ammonia is manufactured by combining hydrogen and nitrogen gases, and I'm given this equation. What volume of ammonia gas is formed if that many molecules are reacted completely? So the first thing that I'm going to do is I'm going to say number of moles is equal to number of particles over Avogadro's number. I'm given a number of particles. Avogadro's number is 6 times 10 to the 23, or 6,02 if you prefer. And you should prefer, I suppose, because that's what's on the information sheet, and you still land up with approximately 0,5 moles. What is the relationship between hydrogen and ammonia? It's a H2 is to NH3 as 3 is to 2. So therefore, I'm going to say 0,5 is to 0,33. Then I take that number of moles. Volume is equal to number of moles times molar volume, 0,33 times 22,4. And I land up with an answer of 7,44 decimeters cubed. Sodium carbonate reacts with hydrochloric acid to form sodium chloride. We've got a certain mass of sodium chloride is recovered after the reaction is complete. And the sample of impure sodium carbonate had a mass of 1,300 grams. Calculate the percentage purity of the impure sample. So first what I'm going to do is I'm going to work out what should I have got from sodium 1,300 grams of sodium carbonate. So I'm going to say the number of moles is equal to the mass over the molar mass, which is equal to 1,300, and the molar mass of sodium carbonate is 106. And you land up with an answer of 12,26 moles. Then you can work out what mass should you have got. So therefore, we're going to do a relationship between sodium carbonate and sodium chloride, and it's a 1:2 ratio. So I'm going to say 12,26 is to 1 is to 2 as 12,26 is to 24,53. And I then say mass is equal to number of moles times molar mass. The number of moles, 24,53, that I would get of sodium chloride. The molar mass of sodium chloride is 58,5. And therefore, I should have got 1,434,91 grams. If I now wish to get the percentage purity, I'm going to say 585 out of 1,434,91 is equal to, and I get an answer of 40,77% when I times that by 100. Last question. 3 grams of zinc is packed into a flask of hydrochloric acid and the concentration is given. Use calculations to determine the limiting reagent, and I've told you how to make sure you at least get some marks even if you can't do very much with limiting reagents. And the first thing is to work out the number of moles of each. So the number of moles is equal to mass over molar mass for zinc, and that's going to be 3 divided by 65,4, and that equals 0,046 moles of zinc. 2 marks. Then number of moles is equal to concentration of times volume for hydrochloric acid. The concentration is 0,5. The volume is 0,1 decimeters cubed. I had to divide by 1,000, and I get 0,05 moles of HCl. But I've got a mole ratio of 1 is to 2. So if I go zinc is to hydrochloric acid as 0,046 is to 0,092, that's much more than the 0,5 over here. So that is not possible. Then we are going to say, what about if I had 0, this is a 1 is to 2 ratio, by the way. What if I had 0,05 here? I would get 0,025 over there, and that is possible. And therefore, it is the hydrochloric acid that is the limiting reagent.